Let's get to it. Enter each equation below into your calculator, which we're not going to do. Odds are this is going to be a non-graphing calculator unit. And be the graph. Fill in the column for each question. Okay, here we have the equation y equals 3. Well, it's giving you this chart on how to identify what type of degree are we dealing with and classifying it by the number of terms. If we don't see an x value here, then that's going to be a constant. So this must be a constant. And there's only one term, so it's a monomial. Quite possibly the easiest part on your next test truly might be they might give you a function and you just have to look at it and identify, is it a monomial, binomial, or trinomial? Or they might give you a function and you have to just simply identify, is it a linear, is it quadratic, is it cubic, quintic, quartic? It just takes committing that stuff to memory. It's really not too difficult. Number of terms here, we're going to have 0 terms. Y-intercept as a coordinate, it's going to be 0, 3. Now, if you had to graph this, which they want you to do here, y equals 3, that is going to be a horizontal line going through the y-axis at positive 3. That's what it looks like. Next, x plus 1, 2 terms, so binomial. Now, when I identify the x, I notice that it doesn't have an exponent that we can see, but it has an exponent of 1. Therefore, it must be linear. It's a first degree polynomial, so it must be linear. Number of terms, 0. Y-intercept as a coordinate, 0, 1. And if you were to sketch a graph of this, it looks something kind of like that. Notice the arrows are going opposite directions. One's going down, one's going to go up. That's going to be some important information here in just a second. Here we have a monomial. There's only one term. I see an x that's being squared. Therefore, it must be a second degree polynomial. And we call second degree polynomials quadratics. I misspelled that. Quadratic. It's quadratic. That's what we say down here in West Texas. It's quadratic. Sorry, y'all. Quadratic. Math teacher, not a spelling teacher. Number of terms. This is going to have one term. Y-intercept as a coordinate. Let's go with 0, 0. And if you were to sketch a graph of this quadratic, it's going to look something like this. Notice the arrows are now going the same direction. Both of them are pointed up. It indeed has one turn. See, it goes whoop, one turn. All right, move over to the next side. Easy stuff so far, I hope. All right. Here we have the equation y equals x cubed. Well, there's only one term, so it must be a monomial. Since I have an x that's being raised to the third power, that's a third degree polynomial, therefore it's cubic. Cubic. Number of terms, 2. Going to have at most 2 terms. Y-intercept as a coordinate, 0, 0. And if you were to sketch a graph of what this would look like, it would look something kind of like this. Notice the arrows are going different directions. One's going down, the other's going up. Here, oh my gosh, there's 1, 2, 3, 4 terms. So that's a polynomial. Now we see an x that's being cubed, one that's being squared, and then one that's being raised to the first power. Identify the biggest one. That's what tells you what type of function we're dealing with. That's a third degree, so it's cubic. Number of terms, 3 minus 1 is 2. Y-intercept as a coordinate, oh, look at that 4 right there, 0, 4. And if you were to sketch a graph of this, it might look something like this. 1 turn, 2 turn. Notice those arrows are going opposite directions. This one here, I'm going to go speed through this one a little bit. We're still dealing with a polynomial, still cubic. But since the leading coefficient is negative, now it's going to look more something like this. My y-intercept's a little off, but the important thing is that you realize that the arrows are now going, one's going, rather than going down and up like this one's now going up and down. Our end behavior is different. This one right here, we're going to skip it, but I'm going to give you the major details. It is a monomial, and it is a quartic function. But let's move on to this one. I don't really like that example. I like this one here. We have 1, 2, 3 terms, so it must be a trinomial. Looks like the exponent with the biggest degree is 4, so this is a 4th degree polynomial, therefore it is a quartic. 4 quarters in football, 4 quarters in $1, so a 4th degree polynomial must be a quartic function. Now, let's see. Oh yeah, how many number of turns? 4 minus 1 is 3. Hopefully you're picking up on a pattern. What do I want you to do here? Y-intercept 0, -2. And if you were to sketch a graph of this function, it looks something kind of like this. Notice the arrows are going the same direction. Both are going down. The reason why they're both going down now, well, for a couple of reasons. One, it's an even degree polynomial, but since it's a negative leading coefficient, then we must be ending at positive infinity. This one here, we're going to speed through this one. Monomial, quintic. Let's now go to this one. Trinomial, because there's 3 terms. The variable with the largest exponent is 5, so this is a 5th degree polynomial, therefore it's quintic. Quintic. Let's see, how many turns? 5 minus 1 is 4. Y-intercept 0, 0. And if you were to sketch a graph of this, it looks something kind of like something like that. My arrows are going opposite directions, down, then up. And we have 4 turns. 1, 2, 3, 4 turns. Move on to the next side when you're ready. Okay. Now today we're going to be dealing a lot with something that's called end behavior. And end behavior, I guess a simplified answer is for end behavior, what are your arrows doing? Okay. Here, our arrows were going down, up. Notice it's an odd degree polynomial. Here, down, up, odd degree polynomial. Here, up, down, odd degree polynomial. This is a 3rd degree, but now the leading coefficient is negative. Therefore, your last arrow must be ending in negative infinity. And then here, this is a 4th degree polynomial. Notice that the arrows are both going the exact same direction. Here's the takeaway. If it's an odd degree polynomial, your arrows are going to be going opposite direction. Think that. Think odd, opposite. Odd, opposite. And if it's an even degree polynomial, that means your arrows are going to be going the exact same direction, either both pointed up or both pointed down. Oh, vocabulary. Put a negative there and a positive there. The end behavior of a polynomial function's graph is the behavior of the graph as x approaches negative infinity or positive infinity. The leading coefficient and the degree of the polynomial is used to determine end behavior. So odd degree polynomials with a positive leading coefficient generally look like, if it's odd degree, where you know they're going opposite, and if the leading coefficient is positive, that means the last arrow must be pointed to positive infinity. So my arrows are opposite. The last one's going to positive infinity, so they tend to look something kind of like that. So its end behaviors are down, up. That's its end behavior. And the way that we're going to fill that information here, this is what this is saying. As x approaches negative infinity, so as x is getting smaller, y is also getting smaller. So as x approaches negative infinity, y approaches, that's pointed down. So we're going to write negative infinity here. And then it picks up here. As x approaches positive infinity, so now as x is getting bigger, y is also getting bigger. So as x approaches positive infinity, that last arrow tells us what y is doing. Y also approaches positive. Next, Odd degreed polynomials with a negative leading coefficient. So odd, the arrows are going opposite direction. The leading coefficient is negative, so the last arrow must be pointed to negative infinity. So they're going opposite directions, and odd degrees could look something like that. This in behavior is from left to right, up, down. So in this blank, I'm going to look at that arrow up, so positive infinity. This blank, I'm going to look at that arrow, it's pointed down, so negative infinity. So as x approaches negative infinity, y is approaching positive infinity. As x is approaching positive infinity, y is approaching negative infinity. As x is getting smaller, y is getting bigger. Here's x is getting bigger, y is getting smaller. Even degreed polynomials with a positive leading coefficient generally look like, well, even degree, so your arrows are going the exact same direction, positive leading coefficient, so it kind of stands to reason they should both be pointed up. And it could look something like this. Both of those are pointed up. So hopefully you're aware of the fact that in these blanks, these should both be positive infinity. Next one, the even degree polynomial with a negative leading coefficient, even degree, so same direction, negative leading coefficient. So both of these arrows are going to be pointed down. And an even degree polynomial with a negative leading coefficient could look like that. Its in behaviors are down, down. Both of those arrows are pointed down. So now we can fill in these blanks. Negative infinity, ooh, positive, and ooh, negative infinity. They're both going to negative infinity. All right. Looking at example 1, describe the in behavior of the following functions. Locate the variable with the biggest exponent. There it is. This is an even degree polynomial, fourth degree, quartic. Even degree means our arrows are going the exact same direction, either up, up, or down, down. The way you can tell, well, which one is it? We'll look in front of the x to the fourth. It's positive. So therefore, our arrows must be going the exact same direction. And now we can fill in these blanks. Since both those arrows are pointed up, you're going to do positive infinity in both of those. Example 2. Locate the variable with the biggest exponent. There it is. That's a fifth degree, odd, opposite. So we're either going down, up, or up, down. The way you can tell is look at the leading coefficient, which is negative, which means the last arrow has to be negative. So we can get rid of that one. Our in behavior is up, down. So in these blanks, we're going to put positive infinity, negative infinity. Example 3, locate the variable with the largest exponent. In fact, I want you to do 3 and 4 on your own. See if you can do them. Give you about 30 seconds. That's what you should have. This is a fourth degree, even. So same direction, leading coefficient is negative, so down, down. Here, this is a fifth degree, odd, so we know they're going opposite. Since the leading coefficient is positive, that means the last arrow must be going to positive infinity. So down, up for that one. What do you think so far? Really not a lot of math. Just going to be some things you want to commit to memory. A turning point, maximum number of turns. I've sort of already given you a little clue as to find the maximum number of turns. It is n minus 1. That's the formula, if you will. Whatever the highest degree is, subtract that number by 1. That tells you the maximum number of turns your graph is going to have. So if it's a fourth degree polynomial, you'll know at maximum it's going to have 3 turns. All right, now list all the information you can to determine the equation of the function. For example 1, you would probably want to multiply all that out, which I did the work. That's going to take some time, okay? If you multiplied out example 1, this is how you would do it. We've been doing this since I think unit 4. This is what it's going to look like in standard form. So now we can begin entering all these blanks. Degree, the highest exponent here is 3. So this is a third degree. Classify by degree, that would be cubic. Classify by number of terms. Well, there's 1, 2, 3 terms, so that's a trinomial. Our leading coefficient is -1. Maximum possible number of turning points, third degree, subtract 1, so 2. General end behavior. This is where you're going to want to use the arrows, okay? Now, since it's a third degree, we know they're opposite, either down, up, or up, down. The odd degree tells you that they're going opposite directions. The leading coefficient now helps us narrow it down to which one is it. If it's a negative leading coefficient, then you have to be ending in negative infinity. So our end behavior is up, down, and then the y-intercept, there it is right there, 0, 4. This one here, not written in the correct order, but it's not going to take much to rearrange it. This is also a third degree, making it a cubic function. There are only 1, 2 terms, so it's a binomial. Our leading coefficient here is -3. Maximum possible number of turns. Let's take that third degree there, subtract it by 1. We're going to get 2. And your end behavior for this one is going to be the same as the previous. Y-intercept 0, 7. What degree is example 3? What do you think? Good. It's a fourth degree. That one's not in the correct order. And odds are, if they give you a question on your next test where they want you simply to identify the type of function, it's probably not going to be in the correct order. So check that. So yeah, fourth degree, that's a quartic. 1, 2, 3 terms, that's a trinomial. Looks like our leading coefficient is +2, positive being the most important thing. Maximum number of terms, fourth degree, -1, 3. General in the behavior. Since it is a even degree polynomial, they're going the exact same direction, either up, up, or down, down. How do you know which one? Look at the leading coefficient. It's positive, so it's up, up. Our y-intercept here is 0, 7. All right, flip over to that next side when you're ready. I want you, here's how we're going to end our lesson for today. These two that I've highlighted, try to fill in all these blanks. And when you get to this point here where it says graph, you just match it based on your function, which one of these graphs. I'll give you a little bit of time to work on that. All right, let me go over this last one here. Hopefully you're able to fill in the majority of this on your own. When it comes to matching graphs with the function, I like to start with, well, which ones could it possibly not be? And I'm first looking at in behavior. I'm looking at which graphs, if I'm going to eliminate some options here, which ones do not have in behavior up, down? Well, this in behavior here is up, up. So this one's eliminated. This in behavior is up, down. So maybe. This in behavior here is down, down. This in behavior is down, up. This in behavior is up, down. So we've narrowed it down to two possibilities. I would then look, well, how many terms does this one have? This one has 1, 2 terms or terms. So while this is still positive, it's probably not that one. This is probably a third degree function because how many terms does a third degree function have? 2 at most. And then I look over here. How many does this one have? 1, it's kind of hard to tell, but 1, 2, 3, 4 terms. This one has 4 terms, which by the way is the maximum amount that ours is going to have, 4 terms. All right, submit. We have a lot of notes today, so just take a photo of this last page. Submit it on my Canvas, Unit 8, Day 2.